So let's start on time. Hello and welcome to our second NFDI ToolTalk. One notice, we are currently streaming live on YouTube. So today the talk is hosted by NFDI for Inc. and they will present us their data management tool, Shepard. So I'm happy to welcome Florian Krebs on stage. He is from Deutschen Zentrum für Luft- und Raumfahrt, and I think after the talk we will have some time for all of your questions. Please take over.
Good afternoon, everyone. I'm happy to introduce you today to Shepard, our storage for heterogeneous product and research data. It's a data management system we've been working on for a couple of years now. And today I will show you what this system is all about. So, of course, it doesn't change the slide. So first of all, I want to give you a short introduction to German Aerospace Center and the Center for Lightweight Production Technologies, where I am working at. Then I would like to show you our intrinsic motivation for experimental data management. That means data that is coming from actual physical experiments. This is our definition of experimental data management. You could also think about it other ways. Of course, then I will go into a little bit the technology, so the architecture and technology stack of the data management system. Afterwards, I will show you a selected use case, in our case, thermoplastic advanced fiber placement. After that, I will talk a little bit about automatic data contextualization, because in my opinion, data without context is actually worthless. So you need to know what has happened, why it has happened, and what happens after and what happened before. To make actually any sense of it. And then I will show you a little bit about the analytics capabilities, which can be integrated in Shepard. And afterwards, I give you a short summary and outlook. So let's start. The German Aerospace Center is probably known to most of you as the German NASA, sometimes it's called. So in a sense, we are a big research institution, but also the German Space Agency, and also have a project management agency under our belt. Today, I will talk about the research institution part, especially in the field of aerospace or aeronautics, where the Center for Lightweight Production Technology is part of. So in a nutshell, what are we doing at the ZLP in Augsburg? Well, we try to come up with production solutions for current and future aerospace applications. In that regard, we have a lot of different robotic cells, and we try to automate different processes that are currently used in aeronautics or aerospace applications and are currently still dominated by manual labor. So our main research interests in Augsburg are manufacturing technology, especially regarding CFRP, so carbon fiber reinforced plastics, also assembly and joining technologies to make bigger structures, like, for example, this helicopter frame. Of course, as we are working in aerospace, everything has to go through quality assurance, so we need to find methods to actually integrate quality assurance within the manufacturing process and not just afterwards. And actually, I am leading the group on flexible automation systems. So as we always have different projects, so this 1 year we're building a rocket booster tank for the Ariane 6. Next year, we're building a part for a helicopter. And another year, we're building a part for the A350. So we have to be very flexible within our machines and have to be able to change easily from one part to another. But that's not the topic of today's talk. Today, I want to talk about data management. So, of course, during all of these experiments, there's a lot of data that's being gathered, that's being produced by these machines. And we always were quite unhappy how this all worked out, because a lot of these different machines had some capability to produce a CSV file as CSV file, for instance, for time series data, but still this was quite a hassle. And if you have a lot of different devices, it gets difficult to coordinate all the devices and which data belongs to which trial. So we thought about building a data management system. Oh, sorry, I forgot. This is one of the current examples our multifunctional fuselage demonstrator, which has been produced by thermoplastic advanced fiber placement, which I will actually go into a little bit later into the talk. But just to give you an example, this is actually a glorified tape dispenser, and it just lays up all this Scotch tape, this black Scotch tape, along the mold, and produces a part this way. Anyway, data management is easy. So you have a research project, you collect a lot of data, you put it into a database, and then you're done. Great success. Well, unfortunately, as we all know, it's not that easy. Data management and research project is usually a very difficult as there are very many different types of data that have to be managed. Some might actually come from a preliminary design for aircraft. Some might concern themselves with material data. Others are CAD models, then of course numerical models, and experimental measurements that are produced during a production run, for example. Of course, there's also reports and publications that are being compiled, as well as a lot more source code that is getting more and more important. And then, of course, also media, images, and videos that are produced for presenting the project, and a lot of different things we're currently not thinking about. So in a way, a research project generates very many different data artifacts during its life cycle. And of course, artifacts is here not the negative connotation that something is wrong, but it's just some kind of tangible product that is produced during an experiment. As I said, I will focus today on experimental measurements, but just to give you an even bigger picture, the biggest challenge we are currently facing is that all of this data goes to a lot of different destinations, from external storage devices like USB sticks or hard drives, network shares, on your local computer, in the intranet at German Aerospace. As some people print their results. Source code is usually managed in a source control management system. And of course, then you have the employee who also gathers a lot of data. And the biggest challenge is actually he or she is currently the main index. So he or she knows where this data is. But if this employee leaves German Aerospace Center, this data might be actually very difficult to recover, if not impossible. So this is why we thought about Shepard as a system to store heterogeneous product and research data, which is actually available on GitLab as an open source project. So contributions or users are always welcome. And the basic idea was to have a system for data management for active research data. That means data that is still being worked on, that is not crystallized in a sense that it's ready for publication, but we're still working on this data, working with this data to generate more insight. So what were the basic design considerations? We tried to have a highly modular design that easily allows you to integrate different payload databases, let's call them this. For example, time series databases or file databases or databases for structured documents or JSON documents for the techies here, but also source control systems or other databases. Then again, we wanted to have a web-based management interface to actually make it very accessible, not needing to install any separate clients on your machine and keeping them up to date, but you can just browse to a website and work with the data. And then we said, okay, everything we want to do, we want to encapsulate within a REST API to allow also custom analytics, which take data through the REST API from the payload databases to your custom analytic application. I will show you later a little example about this. And on the other hand, on our shop floor, we have a lot of different devices which speak a couple of different protocols. OPC UA is one of the more modern ones, but still we need to collect this data and put it into the REST API to put it in the payload databases. Then why are we dealing with a lot of different payload databases? Couldn't we just use one large SQL database or something like that? At least in our opinion, no, that's not an option, because first of all, we wanted to remain as schemaless as possible. That means we want to be able to easily incorporate additional types of data without having to change anything in the system other than the integration part of this data. And on the other hand, for example, time series databases allow you to do magical things with time series. For example, just to get just a small example, just to have normalized time series data, for example, have 100 millisecond buckets, but your data doesn't actually come in this frequency. Time series databases have the capabilities to do this on their own, interpolate data, and also slice the data in the right fashion. And you do this all in database, so it's a lot faster than doing it on the client side. Not even mentioning having to transfer the whole data set beforehand and then filtering it, which makes things a lot smoother to work with. So regarding the IT infrastructure or technology stack, as I said, we are trying to work with a very modular approach. Our organizational database is a graph database based on a Neo4j. For time series, we use InfluxDB, a common standard time series database. For documents or artifacts, we use mongodb. So documents means, in this case, structured documents, and artifacts is usually files. And for the backend, a classical Tomcat Jersey application, we have implemented classical Tomcat Jersey application, and the front end is just a Vue.js application. What important consideration was that well, not all components, but most of these components offer an enterprise model for long-term support and also scalability. That allows us to actually guarantee the performance of the system for a longer period of time, not just the time it's maintained on GitLab. And of course, we're using a lot of GitLab's features like continuous integration, continuous development, for example, to generate automatically the client libraries for different programming languages, and also deploy the most recent version to our host machines. So going a little bit deeper into the system, looking at the universal data model. So our data model is actually very simple. We try to have a very open-ended model, which allows a lot of customization by the user. So just to give you an example, so we actually only have two main types of objects. So a collection is a collection of a lot of different data objects. And data objects can be organized in a hierarchical fashion. So I can have a data object which contains another data object, which contains another data object. Well, it's not really contains, it's more like a parent-child relationship. But additionally, we also have a predecessor relationship, which allows us to say these four data objects are a predecessor for the next following data objects. So it's easily to browse also by some kind of logical sequence of things than just having a hierarchy of different objects. And of course, if you, for example, have something like automated tabling, maybe you know, usually your layer consists of different layers. So each layer consists of a lot of different tracks. And these tracks are each pass of the head of the robot over the mold. So in the use case I will describe later on, we decided to have each track as our most granular unit. And of course, they are all these different tracks are children to a parent object that is called, of course, layer 1, for example. And all these layers are then children to an object that is sorry, That is the general layer object. And of course, each object can contain different types of references. So we have this basic reference, which is, well, the basic reference type we have, which is basically just has a name and a reference type. But then it reflects all the different types of data we can work with currently. For example, we have a time series reference, which has additional attributes like the actual time series it's describing, and also when it started and when it ended. This is important as Influx, for example, sees time as a very continuous thing and doesn't really discern between these different steps, for example, within a process, but it actually wants you to always have a start and end time. Structured data references are just references to documents that are in a specific JSON-oriented form, and files is pretty self-explanatory. Well, we are referencing different files there. As I said, collections consist of these hierarchical data objects. Data object itself can belong to different collections. For that, you can use data object references. This is a special type of reference which allows you to reference a data object. This is, for example, in your first collection. And of course, data objects refer to data sets, for example, time series, structured data, or file references. And from there, we represent this data model within our Shepard API, which is based on Open API standard 3.0, which makes it easy to work with as long as you're familiar with classical REST APIs. And by doing this, we can work with the system in very different ways. Of course, there's always the possibility to use our web interface for manual data input. From our point of view, this is usually not recommended. It's very error prone and, of course, very inefficient, because somewhere this data was already gathered and now someone has to type it in manually. So we usually go to scripted interaction, for example, using a Python client library or Java C++ library. And, for example, import data this way, for example, from your hard drive to the system. Or for a live acquisition of data, we can also integrate with foreign tools. One example is on the following slides. And just a small addition there, we also have a subscription model within Shepard, which allows you to react on data changes. For example, if there's a new data object, a separate system might be notified, there's a new data object. Do you want to do something with that? Of course, the system can decide what it wants to do with it, but we used it, for example, for automatic conversion of data from a vendor-specific format in a neutral format, that when someone uploaded a file in this vendor-specific format, it was automatically converted in neutral format, so everyone could use it more easily. So coming back to the use case, as I said, we have this robot here with its tape dispenser and laying up the carbon fiber tapes. Then we also have a camera system watching the whole process. And of course, we have to lay out each layer, each track by itself. And of course, the system consists of a little bit more than just the robot and the camera. It consists of a controller for the robot. It consists of a controller for the cell. This is a typical programmable logic controller. Same with the head for the robot, also programmable logic controller. And then we have a customly written controller for a camera system. And as you can see, there's a lot of different interfaces within the process itself. I'm not describing the safety component today because this is not the scope of the talk. But as you can see, the cell actually talks to the robot and looks if everything is in order. The robot itself talks to the head and tells it when to start or stop layup. And at the same time, it talks to the camera controller and sorry. and basically tells it also when to stop data collection. And on the lower part of the picture, we're actually seeing all the connections necessary for the interaction with shepard. So in our case, we decided on using OPC UA as a standard interface for shepard, but of course we can use a lot of different protocols. This is just one example there. And all these OPC UA clients actually deliver their time series data through to this OPC router program. This OPC router program is actually a commercial tool I mentioned by InRay Solutions. And basically what it does, it just converts this protocol from OPC UA to REST calls and can put them into the shepard database. But at the same time, we have this context provider. This context provider actually watches the whole cell and decides when a new track has started and decides when a new layer has started. And of course, it also enables this, gives this information, for example, to the camera controller to be able to add this data. To clarify that, I have a different presentation, different slide here showing all this. So first of all, as I said, we are capturing the time series data using OPC UA. And having this data aggregator called OPC router, which aggregates this data and puts it into the REST API, which in turn puts it into shepard. And by the way, our time series data collection currently is always on. So unfortunately, sometimes something happens when you're not doing an official experiment, but you just did something, and we wanted to prevent this kind of out of context data loss. So we're always collecting this data, even if there's no experiment running. But using our context provider, we actually watch the KRC4, the robot controller, what it is doing. And by watching the robot controller, we can actually discern, now it's doing the next track, now it's doing another layer, now it's doing quality assurance. And by watching this, we can manage the process context and actually generate individual data objects for each track and layer, and also the hierarchy between them. And as I mentioned, the camera system actually uses this context to put artifacts into the REST API using event-oriented protocols. So this means, for example, in this case, the camera actually watches or captures a whole track during the layup, and when this track is finished, actually the whole picture is written to the REST API. But to do this, actually, it needs to know where to write it to. And this is what the context provider is actually for. And of course, as I mentioned earlier, the REST API also allows you to access the data you just put in. For example, to do some analytics using Jupyter notebooks, for example, or in other cases, used to provide live dashboards of your process. And of course, all these analytics results can be written back using the same REST API calls to capture this in shepard. Just to give you a quick look into the web application itself. So it's actually pretty straightforward. You have your shepard front end. And for example, you see here an object called layup. And as you can see, it contains a lot of layers. And this layup, of course, has just doesn't have a predecessor and successor, but it has a parent. This is actually the experiment name. And you can see the different layers. Unfortunately, the name ordering is not working correctly yet. I already opened an issue for that, but people are working on this. On the other hand, this UI is actually not meant for deeper analytics. It's meant for basic management tasks. On the one hand, of course, user management. On the other hand, simple modifications. For example, if you want to change the relationship between different data objects, you can do it in the web interface more easily than doing it by the client libraries. But it offers a first glance of the captured data and allows us quick plausibility check and completeness check. But currently, we're also having a couple of plans to use machine actionable research data management policies to automatically validate input or existing data sets to be able to see if all the data has been captured, which we actually wanted to capture. And just a quick reminder, currently we don't support versioning yet, but we have a new project where we will look into versioning support for different data objects, but we haven't specified the scope yet. For integrated analytics, of course, you can use Jupyter very easily. As you know, Jupyter notebooks are not as programmer unfriendly as other libraries, but still you do Python programming there. And the API actually integrates seamlessly with Jupyter. So you just use this client library as you use any other Python module. And then you can, for example, produce these state force graphs. I will walk you through an example afterwards. This is just a small example for interactive plotting, but currently we're also looking into more complex applications regarding artificial intelligence or more specifically machine learning methods to, for example, do classification on these time series. So giving you a short summary and future outlook, as I've shown, Shepard is an open source data management solution for heterogeneous data from different research activities. You can structure data in Shepard in user-defined ways, so we don't have a lot of basically we give you a lot of freedom to organize the data how you want to work with it. On the other hand, we provide a common interface for easier reuse of acquisition and analytics tools. And of course, it can be easily extended with multiple additional data sources. For example, if you're using geodata, you might have to write a plugin for the backend, but then you could also use geodata within Shepard. As mentioned, it's already open source available under the UL. And currently, the main technical extensions we're currently working on is search capabilities. So we want to be able to search within the data, not just only the describing metadata, for example, like name or dates, but also within the payloads. This is actually a challenge with time series because we're not quite clear on what we actually want to search there. Then secondly, we're working on a permission management system, which allows users to specify who can access which data. Currently, it's a very open system, which everyone shares its data with everyone. But of course, we need some kind of limits to that. And last but not least, metadata integration is becoming more and more important. And we're looking into ways to enable Shepard to interact or work with fair digital objects through metadata more strongly. Thank you for your attention. Do you have any questions so far? Otherwise, I would go into a presentation to show you a little bit of an example.
Thank you also from my side for this interesting and deep insights into Shepard. Yeah, so if there are any questions yet, you can just raise your hands or write it in the chat and I can call you. If not, we can have a look at your demonstration. There is one question from Timo Mühlhaus.
Hi, thanks for the nice presentation. Looks fantastic. Maybe it becomes clear in your demonstration later. I was hesitating to ask the question, but what I did not get is, how can you structure the data? I understand that you get everything back as object, but you don't know what you get, right? Because it can be from the file source or from the time series database. So this I did not understand.
I see. So when you put in the data into Shepard, for example, a time series, you have to refer to a specific endpoint, for example, the time series endpoint, and this is how it infers this is time series data. If you're using the file endpoint, this is file data. And of course, when using this endpoint, you have to specify, okay, this is related to the following data object. And this is how it organizes the data. But we will look into the web UI, then it becomes probably a lot clearer.
Okay, thanks.
All right, I have to. Any further questions? All right, I will switch to my browser. So as you can see, this is the same front end as you saw on the slides, and I already selected the AFP collection for advanced fiber placement, and we have one of the experiments there, the intermediate demonstrator Bly group 1. And if I look into this now, I can see, okay, this one has 1 children, it has no predecessors, no successors, no references, but it has, as I said, 1 children. This is this layup object. And under this layup object, we have actually a lot of different children. There's all these different layers. And for example, if I go to select layer 8, I can see that it has 1 predecessor. It doesn't have a successor. That's still a mistake on our part. I selected just 1 randomly, and I see that there's still something missing because it should have a successor. But anyway, if I go into the children here, I can see, okay, there's around 165 tracks. And if I look into one of these tracks, I can see that this has actually a lot of different time series contained within, which are within a container, but this doesn't really matter there. Unfortunately, I have probably have selected a bad example because it doesn't have a file reference. Let me go back there. This has successes in there, and it has children, and we have a track there. And as I said, again, the same time series. Of course, we have the same process settings for each of the tracks. So we have different temperatures, for example, different positions, a lot of different time series there, and also different files here, for example. And as you can see, this is, for example, one of the images the camera took. If I download this, unfortunately, it's a TIFF file, so you won't see a lot. It's a 16-bit TIFF file, but there is data in there. Just to make it more clear, I'm getting the CSV file, which you can probably see the CSV file because I don't share my whole screen. This is empty. Camera settings. I hope people collected data there. There's a beautiful CSV file. And this is how this data is actually organized. And if I want to work with this data, I will walk you through a Jupyter notebook of mine, which is actually used for this plotting example I had there before. Basically, first, of course, you need to specify some configuration information, which system I'm working on. Of course, we have a couple of them, a couple of smaller helper functions to define the API key, which is used to access the system. If you're looking into my user tab, you can see I have 2 unnamed API keys. I'm usually quite lazy there. But you need an API key to talk to the system, so you don't have to use your credentials like username and password. But the API keys also can have a limited validity, so it's easy to remove access. And then we're importing our IDMS client library. And full disclaimer here, this still uses an older API, which still has a project, experiment, and step API. This all has been consolidated in a digital object API, but basically works the same. And then we have this influx reference API. And this call actually gets all of the projects we have in the system. So project API get all projects. This might be not a good idea if you have hundreds or thousands of projects, but in our case still works. And then this is just a couple of widgets which allow you to select, for example, a certain project there, select a certain experiment, select a layer, and select a track, and then let's use something different. For example, let's see how the robot moved. This is, for example, motion data from the robot. It's while it was laying up the track. And of course, I can easily view each track there by itself. But of course, using the same logic as I used there, I could also do an overview for a whole layer. But then it gets difficult because actually this data set contains about 3,700 tracks. And when I migrated it from our first version to a second version, it was actually 20 gigabytes of time series data. So you might have to think about how you analyze your data there. But this actually concludes my presentation on the Jupyter notebook. Of course, I can go into a lot more detail there, but for anyone who is a little bit familiar with Jupyter, this might be quite easy. Usually it boils down to calls to the API, like this is, for example, where I get the influx reference attachment, so the time series, and I give it the project value, the experiment value, the track value, and which time series. And then of course, I get the timestamp, I get this additional variable, and the selected variables I have here. Thank you for your attention.
Yeah, thank you so much for also this live demonstration. We got one more question in the chat in the meantime. Volodymyr Kushnarenko, do you want to tell your question and unmute, or should I just read it? I can also do that. Okay, so where do you store the file? In Shepard, or is it only reference to the source? File migration, is it a problem for big files?
Well, so first of all, files live, for that I'm going back to my presentation just to go back to the technology stack. So to store files, we're actually using MongoDB and the griddfs extension. So all files live within a separate database. Why are we using griddfs? Because MongoDB can only store 16 megabytes of documents. So you would have to do something. On the other hand, griddfs is basically limitless. So you can do very large files. But on the other hand, if you're working with very, very large files, it really depends what kind of file it is. If it's just a very big, let's assume it's a 500 gigapixel image, which you have to collect as a whole, you might have difficulty working with that because you always have to load the complete file. And in that regard, I would actually suggest to split up the file in some kind of grid or pattern that you can easily access separate parts. On the other hand, we already worked with ultrasonic scans, which had around 20 gigabytes, and it still worked, but it's getting slow. But that's more a bandwidth than a limitation by the database.
So thank you for the answer. Yeah, there's also thanks in the chat. Any other questions or feedback? Yes, one more question, Timo Milhaus.
Me again. Hi. No, actually, the question a little bit stayed the same. So you in your Jupyter notebook application, you somehow try to access. I think it was VC on part or something. How do you know that the object you get back has this attribute?
Okay, this is of course a simple example, and I know I put this there, but how do I know that? This is I can find this out by looking into for example, into the collection and just finding the right one, this one. And I just need one of the time series examples. I need one of the tracks and the time series. And this is one of the, there is the VC on part. Of course, I can get all these, the list of all these variables I put in as time series, also by the API. Actually, I'm doing this. If you can see here all these symbols, I got them by this one here. This is where I actually get the reference and not the data yet. And there's already the metadata, which time series are contained there. I'm just putting all these options there. And of course, the timestamp is given, as I always have this. And the VC on part is actually something very specific to this thing where we needed this. Basically tells you if the robot was already on the part or not.
Yeah.
But in the end, actually, you get all this information that there is a timestamp, there is something called VC on part, and there's other things just by calling the reference and looking into the reference object.
Okay, so the schema is somehow a property of the data under the organizational database. Do I understand this correct? So there the data are somehow schematized, and then you pass them through how they are.
Yeah, but on the other hand, we allow for a lot of different schemas to be specified. Of course, time series has some typical elements like timestamp, like value, like unit, and these things. But regarding structured data, it can be any valid JSON you want.
Okay, I see. And then you pass this structure through your layers. Okay.
Exactly.
Yeah, cool. Okay, thanks.
And of course, this is something very different from the first tool talk. It's not that research data management oriented as the ARC system was. But on the other hand, it gives us an opportunity to start at the bottom and work our way upwards.
No, I think that's why I'm asking. So we could lay our ARCs under your organizational database in principle.
Yeah, I guess.
Yeah, cool. Thanks.
That should work.
Any other, maybe last question? If that's not the case, we can even end before scheduled time. And yeah, a big thank you to Florian Krebs for the interesting talk, and to you all for participating. So I hope to see you back in a month. The next talk is hosted by GHGA, and they will give us some insights into their pseudonymization and record linkage tool, Mainzelliste. So hope to see you there, and goodbye for today.
Goodbye.